That should be. Well, looks. No. Okay. That should be good. All right, and then back to here. Or you gotta go. Yeah, go there. This one. And then programs. This one. Yeah. And no, just click program. Don't click program. Program. Yeah. Okay. Present. Okay. Can you check?
Yep. Okay, so what is RCC? RCC is roller compacted concrete. So roller compacted concrete, it's basically what it sounds like. We have concrete, we use a roller to obtain density and make it dense. And the reason we do this is because it's typically a drier mix, as you can see down here. It looks a lot more kind of like dirt that's really, really dry, and so it does have a low cement content and typically a low water to cement ratio, so it is very dry, and we use the roller to achieve density, and that way we can use aggregate interlock to mainly get our, or to help increase our strength. So why are we interested in this? Well, recently it has become more relevant as we push for sustainability. I'm sure you've all heard of this because it's basically the reason we all have jobs, well, at least most of us. So the push for sustainability, RCC is good for that because it typically has a low cement content. Cement is it's the highest cost of, or it has the highest cost of most of the constituents of concrete, and it is the most, it has the most emissions to make cement. So there we're lowering costs, we're lowering the emissions to the world, and then so because it's such a dry mix, you can open it more quickly to traffic in terms of a pavement because you don't have to have the long hydration time. But with that, there are a few issues. Since it hasn't really been extensively used in the past as a pavement, it is the design for it is a little bit outdated, and it's mainly based on fatigue curves done in the 1980s. So those are a few things that are issues with RCC that we kind of looked into. So going into a history of RCC, it's not a new thing. It's been around for quite a while, mainly in dams and other mass concrete applications. As a pavement, it's typically used in industrial or heavy duties as a heavy-duty pavement. Typically, it's not a very pretty or aesthetically pleasing surface, so it hasn't really been used as a pavement very much, and it's also, scratch that. But the first actual pavement was built, as it says, in 1975 by the Army Corps of Engineers, and it has pretty variable properties. As you can see, the 300 to 600 pounds per cubic yard of cement, that's pretty low. Typical paving concrete has somewhere around 600, I believe, pounds per cubic yard. So it is, like I said, it is a very low cement content concrete, and there have been a lot of studies on using different materials to see how they perform in RCC. So going back to the design of RCC pavements, this is based on work by Tayaji and Okamoto in 1987 when they were with CTL, and this is all based on it is a fatigue-based design, and it's mainly based on the flexural strength of our concrete. And there are some issues with that, which I will talk about as we go. But that's basically how it was designed for a while. And then recently, ACPA started looking at RCC because, as I mentioned, the push for sustainability, they're trying to look at using RCC in more applications now. And so they developed these curves, the dash curves that you see up there, using their own data. And as you can see, they kind of fit along with the results from Tayaji's and Okamoto's work back in 1987. So then they started comparing that with conventional concrete. And as you can see, there's a crossover point where you may need a thinner or you may need a thicker RCC pavement as opposed to conventional concrete. And that becomes a problem because if we're trying to make a sustainable concrete or a sustainable pavement out of RCC and we have to make it thicker than our conventional concrete, then you may actually have to use more cement, and so you're not actually being sustainable. So that can be a problem. And this also reiterates that that last slide where your RCC, you may have required thickness that is actually thicker than conventional paving concrete. And so a lot of work has been done on the properties of RCC. This is I'm going to go through some of our literature review right here. But what we found is that what a lot of people have found is that RCC has a lot of similar properties to conventional concrete. In terms of modulus of rupture, 650 psi is a very typical design value for conventional concrete, and the elastic modulus and Poisson's ratio are very similar to our conventional paving concrete. Further work has been done also on the use of recycled materials in RCC, such as fly ash. In this study, they actually have, as you can see, 674 pounds per cubic yard. That's a very significant cement content. Like I said, typically you're going to have a lower cement content around 300 to 500 pounds per cubic yard. So that's a little extensive, but again, the use of fly ash was it was something a little bit new for this study. And this is, again, reiterating that fact, but this has a slight lower cement content. We're getting more down into the range of what is typical RCC, and a lot of the strengths and the compressive, split tensile, and flexural strength showed similar results to typical concrete. In addition, people have also looked at using fibers with RCC, which is another important thing because typically with roller compacted concrete, you don't have dowels for load transfer, and you're not going to use reinforcing steel. And that's mainly because you have this really dense material that if you put it with it, if you put that with the steel, it's not going to stay in place and work the way you want it to work. And so typically there is no reinforcement with RCC, which adding fibers can help keep some of those cracks that are going to naturally occur with concrete. It's going to help keep those tighter and make sure that they don't erode the pavement more so. All right, so moving on to RCC with recycled aggregates. There has been a fair amount of work with this. People have looked at using recycled asphalt pavements as well as recycled concrete aggregate. There have also been, I think, 1 or 2 studies on slag aggregate and industrial waste sand. One of the more significant ones in terms of RCC was a work done by Sasha and Balbo. And that study was different in the fact that they used RAP, and they also ran they ran a fracture test to help understand how RCC is actually going to perform. And I'm going to talk about why running fracture properties is more important when we're talking about pavements a little later on. But their findings found that the use of RAP can significantly decrease your compressive strength, your split tensile strength, in addition to your critical stress intensity factor and your total fracture energy. Now they use 50% RAP, which is pretty significant, and also their method for compaction, of this RCC was to follow the Proctor test, and this doesn't quite convey what is actually going on in the field when you're actually compacting RCC in the field, where you're actually running a roller over this material. All right, so that brings us to what we actually did here. We really wanted to get up to speed with RCC, try to get our own properties, get our own feel for how the material responds, and we also wanted to run our own fracture properties to kind of relate back to that pavement design question of, do we actually need a thicker or thinner RCC pavement when we're in relation to conventional paving concrete? Again, if we're using a thicker RCC pavement, we're kind of negating the benefits of having a lower cement content because we have a thicker pavement. And so all of these are questions that we were kind of hoping that we could shed some light on as we went. So the first thing we had to start with, we needed to start with our mix design, and we needed to decide what kind of aggregates we were going to use. And so for this, in the class, we actually used, we made mixes with just virgin aggregates, we made mixes with virgin and coarse frap, and then we also made mixes with RCA. And the way we did this was we had to make a blended, or we blended our aggregates to meet a 0.45 power curve. Mainly that's to get your density, because again, density is one of the most important things with RCC. You want it to be really dense to have good aggregate interlock, and we're, with RCC. And so as you can see, we did the best we could with fitting the curve down to the lower side with the fines. It's kind of hard unless you're using the manufactured sand or better sand than what we had available in the lab. And so to get our maximum density for this, we made mixes, and then we ran the modified Proctor test to find our maximum density and also our optimum moisture content. Our optimum moisture content is very important with RCC because it's not designed like typical concrete where you just specify your water-cement ratio. And so we found our optimum moisture content for our frap mix and our virgin mix, and they were both similar, around 146 pounds per cubic yard, and the moisture contents were pretty similar, around 6%. So that brought us to our mix designs. As you can see with the frap mix, we used 16% frap, and that was all coarse frap, mainly because that's one of our excess materials. The fines we typically want to save for asphalt since they're very rich in asphalt and can provide more benefit there. So now that we had our mix designs, the next thing to do was to create specimens to test in compressive and split tensile strength. And this is a little different than typical concrete. With typical concrete, you just have your cylinder mold and you just compact it by hand using a rod. Whereas with RCC, you're going to have a lot more compacted effort, mainly because of that dry mix, and you're trying to get the highest density you can. And so we use this vibratory hammer following ASTM C1435. And as you can see with the specimens here, when they're split in half, you can see that aggregate is really, really close together, which is not, which doesn't quite look like a typical PCC mix. It's, like I said, it's a little more dense. So the next thing, after we made our specimens, we tested them in 14 days for compressive and split tensile strength, and as you can see, those are the results. The main thing to note here is the comparison with conventional paving concrete. So as you can see, we're pretty similar on all fronts, with the exception of maybe the frap RCC, which showed a fairly significant decrease in comparison with the conventional paving concrete. But if we look at comparing virgin versus frap, we notice that the compressive strength does have a significant difference from the virgin mix, but it does not have a significant difference between the split tensile strength. And this is important because concrete, 99.9% of the time, is not going to fail in compression, probably more than 99.9. So tension is much more important when we're talking about concrete, even though people always come back to what is the compressive strength of your mix. So the next thing we looked into was the fracture properties, and this was one of the real important things that we wanted to look at, because it gives us a better idea of how the concrete is actually going to perform. And so to determine the fracture properties, we follow the SEMB test, and that's the setup there. And as you can see, we're using beam specimens, and that presents a problem since there is no standard for creating beam specimens that are RCC. And that's where we helped make our own procedure for making these specimen beams. And we really tried to follow the ASTM standard for making cylinder specimens as best we could. So we made this plate, and then we used the vibratory hammer to compact it using those three spots that are shown there. But now, why are fracture? What's so great about these fracture properties that they can present extra information to us about our concrete? A few of the main things that we really like. A few of the main things that we really look for with fracture properties are the critical stress intensity factor and the total fracture energy. And the critical stress intensity factor is gives us an idea of how the material is actually going to perform. Is it going to behave in a brittle manner like glass, or is it going to behave in more of an elastic manner like a metal? And then the total fracture energy is going to give us an idea, or it tells you the total energy required to create two new surfaces. So if we go back to the test, how much energy it takes to completely separate those two pieces. And so this is the main curve that you get when we run the fracture properties. As you can see, the red is the frat mix and the blue is the virgin mix, and they showed similar results. And when we're talking about fracture energy, one way you can estimate it is by just looking at the area under the curve of both of these. And as you can see, they both show fairly similar results. And if you actually quantify the results, you can kind of see the same thing. What's highlighted here is the critical stress intensity factor for both of the virgin and the frat mix, and the total fracture energy. And again, that fracture energy is the energy used to create two new surfaces. It's it's one of the things that can be useful in creating a mix design for your pavement, because actually I'll get into that in a little bit. But obviously these numbers, they're similar to each other, but what do they mean? Sorry, backtracking. So are they statistically the same in terms of virgin versus frat mixes? And we found that there's not a statistical difference between any of the major fracture properties of the two mixes. But from this, we need to compare to a conventional PCC, because these numbers on their own don't really tell us too much. And so if we look back and compare them to conventional paving concrete, we can see that our critical stress intensity factor is significant, or is fairly higher than conventional mixes that, I believe this is work from Alex Brand, that kind of characterizes specific mixes used by the Illinois Tollway presently. And it's important to note that the fracture energy of both the virgin and the frat mixes has increased. And again, this is important for pavements. Because it can kind of give us a better idea of how well the cracks are going to stick together, and how much energy is going to be required to actually completely separate two surfaces in our pavement. Okay, so from that, we can conclude a few different things. And the main idea from those fracture properties is that if we have similar engineering properties to our conventional paving concrete, then there shouldn't be any reason why we should need a thicker concrete. And again, that's kind of the main thing here, is do we need a thicker RCC pavement than conventional PCC? Because then it's not going to be as sustainable, and then there's not really much purpose in trying to use it. And that's all kind of based on slab tests that were done in the summer of 2012. Which really relates, which we've really used to kind of correlate back to our fracture properties. How does the actual slab perform in relation to those fracture properties? And so they found a good correlation between the two, better than the traditional flexural strength, which is the typical method for designing of RCC and conventional paving concretes. All right. Okay, sorry. So from the summary of all of that first study is that RCC and PCC have similar, or can have similar strength properties, and it can have similar performance. And so it's important that when we are designing RCC pavements that we look at the actual properties and kind of consider them in our design. And the important thing that to highlight is down here is kind of what I've already talked about. If they have similar properties, or if the mixes have similar properties, then they should behave well in the field, and there shouldn't be any reason to have a thicker RCC pavement. All right, so there's also been a little bit more work done here at Illinois with some other materials. I presented mainly on the virgin aggregate and the frap aggregate, but we've also done work with fibers and recycled concrete aggregate, and I'm going to present a little bit on that right now. So the work with fibers, they didn't really show much of an increase in compressive. Yeah, they didn't show an increase in compressive strength. They actually showed a decrease. Yeah, they actually showed a decrease. But again, compressive strength may not be the best test to be looking at when we're talking about pavement design. But in terms of fracture energy, fibers can greatly increase the fracture energy of RCC, which is to be expected, as that is what has been seen with conventional PCC as well. The next is the study on the crushed concrete in the RCC, and this has some interesting properties because of crushed concretes has a high absorption capacity, so it's very hard to get an exact optimum moisture content for it and to create a good actual mix for the design. So this is work done this was work done in the last semester, and it showed great variability in terms of compressive strength of RCC with that recycled concrete aggregate, which which mainly shows the variability in the absorption capacity of that aggregate and how it may not be the best material for RCC, at least in terms of this study. All right, now finishing up, what is the next step for RCC? First thing to talk about is the structural design. It's kind of what I've hinted at for most of the time here. Do we need a thicker pavement? The answer is probably not, assuming that our engineering properties are similar to our conventional paving concrete. Creating the actual mix design can present a problem, as seen with the recycled concrete aggregate due to its high absorption capacity. And one interesting thing is with joints. As I mentioned earlier, you don't typically have joints with RCC, but if we can introduce joints into it, then that might also help help bring it to be even more relevant in terms of concrete pavement. And that's all I've got. Sorry, I really rushed through that. I get nervous in front of you. But if you have any questions or any comments or want me to talk about a bunch of stuff, let me know. So I can go back and highlight anything. Yes.
Good presentation. The last slide actually, they were showing more different styles for compressive strength, right?
Yeah, these there were a few different mixes.
4 different RCA materials, right?
No, they're all the same RCA.
All using 100% RCA and Z, right?
Alex, is that right?
Yeah, group 1 through 3 were 100% RCA.
There are 4 different RCA then?
No, they're all the same. These are,
the fly ash.
yeah, the percent fly ash. Sorry, I wasn't directly involved in this work.
Any correlation with fly ash for that?
Problem is that with variability in the moisture comes the RCA to actually stay. Yeah, the biggest thing we found found that big study was problems with RCA. So if you want to do future work, I have ideas on how we can make that better, but we can't really say much about it. This is class projects.
Oh, yes. Sorry, I didn't mention that, but if you go back, again, when I rush through these things, I kind of forget. But yeah, every time we ran the what I do? Okay, I broke it. Anyway, when we run the fracture energy, we do load it to its top strength, and then we do an unloading curve when it reaches 80% of its peak strength, and then we reload it to get the unloading compliance.
Many cycles, not like a few.
No. I would expect a worse performance than conventional concrete, mainly due to the less cement content holding it together. I could be wrong on it. Alex, do you have thoughts? Fair enough.
They have more chance for branch.
Oh, that's not a bad idea. I don't think you're right, but you could be. You're smarter than I am.
What's the fiber reinforced? Was that work also done here?
Yeah.
What happened there? I mean, lower compressive strength compared to
yeah, we don't typically expect fibers to increase our compressive strength of concrete or really our tensile strength. They do seem to show a great increase in fracture energy, mainly because they are bridging that the gap that you're trying to propagate that crack, and it kind of holds it together. But in terms of compressive strength, it really it showed a slight decrease here, but typically it really has not a huge effect.
So that's basically because of specimen variation, maybe. Like
it could be specimen variation.
It doesn't increase, it should not decrease also. So
yeah.
Statistical variation.
I would think there may be a more technical reason for it, but then you'd have to talk more about senior people that know more than I do. Sorry, I'm just a lowly master's student.
Any other questions for Eric?
All right, sorry I didn't make your lunch a little longer. Like I say, when I get nervous, I talk fast.
Okay, thank you so much. And is the mic still working? Okay, so we missed, because it was muted in the very beginning, the presentation next week will be by John Anderson from Tiger Brain. He's going to talk about airport runway construction in Afghanistan, how they had to change their methods and expedite everything because of the war zone and everything. So it's going to be a very interesting presentation. And the week after that, we'll have Behzad Benia talk on some of his PhD work. So thank you very much and have a good rest of the week. Thank you, Eric. Thank you.